Good morning. Hi everybody. I am Vempati Srinivasulu, Assistant Professor of Chemistry, working at Nagarjuna Government Degree College, Nalgonda. We are studying Carbanions 1, which is in the syllabus of BSc second year, third semester. In the previous classes, we have discussed what are carbanions, how they are generated, what factors stabilizes the carbanions with different examples. Then we discussed alpha hydrogens, different compounds, pKa values which have alpha hydrogens, their acidity, compared their acidity with pKa values. Then tautomerism. What is tautomerism? Which compounds exhibits tautomerism? And tautomerism and tautomerization in different classes of compounds. After that, we have discussed aldol condensation, reactions involving carbanions. What are carbanions? With reactions with carbanion. In our syllabus, we have 4 reactions. One is aldol condensation, second one is a Perkin reaction, third one is benzoin condensation, and fourth one is haloform reactions. All these reactions involving carbanions, reaction intermediate. So in the last class, we have discussed aldol condensation, aldol. So what is aldol? How it generates? With different examples, we have discussed the reaction mechanism of aldol reaction and ketone reaction. Crossed aldol, what is crossed aldol reaction? What are the products, expected products from various aldol reactions? So in this part 4, we are going to discuss about benzoin condensation and Perkin reaction. So these two reactions proceeds through formation of stable carbanion reaction intermediate. So one by one we will discuss in detail. First we will discuss benzoin condensation. So what is benzoin condensation? So benzoin condensation means, in benzoin condensation, the self-condensation of aromatic aldehydes with no alpha hydrogen in presence of cyanide ion as a catalyst to form alpha hydroxy ketone, which is also known as benzoin. So in this reaction, benzoin formation taking place. That's why we call this reaction as benzoin condensation. Okay. So what is happening here is, aromatic aldehydes, when they react with the potassium cyanide or sodium cyanide, you see, NaCN or KCN. So this is a KCN, we have required catalyst. This is in presence of ethanolic medium. So ethanolic NaOH, ethanolic NaCN or KCN acts as a catalyst for this reaction. In this reaction, this is the product. So what is this? It's a ketone. It's a ketone. In alpha group, in alpha carbon, we have hydroxy. That's why it is alpha hydroxy ketone. It is a benzoin. So two benzaldehyde molecules undergo condensation reaction in presence of potassium cyanide or sodium cyanide, giving a alpha hydroxy ketone, which is also known as benzoin. So this is benzoin condensation reaction. Okay, then, so this reaction also written as like this. So benzaldehyde we can write PHCHO also. pH means phenyl group. So two benzaldehyde molecules participate in this reaction by giving benzoin. So what is condensation reaction? We know that. So addition or combination of two or more molecules by eliminating some smaller molecules like water, ammonia, hydrogen or HCl by giving a product is called condensation reaction. It is also a condensation reaction. So in this reaction, two or more different aromatic aldehydes or a glyoxyl undergo this reaction. So generally we observe aromatic aldehydes. Aromatic aldehydes take part in this reaction or glyoxyls. One more thing, this reaction is reversible. If you see the mechanism, each step is reversible in reversible manner. So in this reaction, potassium cyanide or sodium cyanide acts as catalyst, that too in alcoholic condition. So this is something about benzoin condensation reaction. So we see the mechanism. So this is a very important one. So we see the mechanism, what is happening. So in the first step, our cyanide ion, you see, this is a cyanide ion. This is attacking carbonyl group of one of the benzaldehyde molecule. Why? Cyanide is good nucleophile. It is having minus charge and it is having donating character. So that's why it acts as a nucleophile, strong nucleophile. So this nucleophile is attacking on carbonyl carbon. We know that carbonyl carbon is electrophilic carbon. Because of oxygen, because of its high electronegativity, carbon acts as a electrophilic center, plus charge. Okay, on attacking of the cyanide ion at carbonyl carbon, we'll get this type of ion. This one. Cyanide attacked the carbon and the O become O minus. So this O minus abstract proton from water. Why? O minus is unstable. Whenever it acts as a base, base always abstracts a proton whenever, if possible. In reaction condition is possible, it abstracts a proton. So water is there in this reaction. That's why it abstracts one proton from water by giving this type of compound, hydroxycyanide. Cyanohydrin, we can say cyanohydrin. So this cyanohydrin, you see, we have two hydrogens. In hydroxide ion abstracts this H plus. We have two hydrogens, H pluses, this one. So two hydrogens exhibits acidic nature. If O hydrogen attached to the O is less acidic than hydrogen attached to carbon. Why? Because if this hydrogen goes as H plus, the resultant carbanion is more stable by resonance. That's why this hydrogen is more acidic in nature. That's why this hydrogen goes as H plus to hydroxide ion. Hydroxide ion attracts this proton by resulting this type of carbanion. So carbanion is generated. You see, this is carbanion. This carbanion is stabilized through a resonance. You see, this minus charge is delocalized to here. This pi bond is moved to here. Due to electron delocalization, we are getting this one more resonance structure. So this one. So hence it is stabilized. Stabilized carbanion is generated. So this stabilized carbanion, you see this one, attacks another benzaldehyde, especially at electrophilic carbon. So this is electrophilic nature, as we know that. So this is a minus charge. It acts as a nucleophile. This nucleophile attacks on carbonyl carbon, resulting this type of compound. You see this one. So this compound, this hydroxy, in this compound, this hydroxy OH goes, proton shift takes place from here to here. Why? Because this O minus is stable than this. That's why proton shift taking place. So due to proton shift, we'll get this type of compound. One more thing. So that's why, okay, so this carbanion is attacking on carbon by generating this one, and due to proton shift we are getting this type of compound. Then finally what happens, this O minus electrons delocalize here, this Cn goes as Cn minus. So due to loss of Cn, we are getting finally benzoin. You see, this is benzoin, alpha hydroxy ketone. So what is happening? If you observe this reaction carefully, you see this in this course of different sequence of sequential reaction steps, this is slow step. So as we know, slow step is a rate determining step. That's why this reaction rate is depending upon aldehyde molecule, both aldehyde molecules and cyanide molecule. That's why it is this reaction order is 3. Okay, this is slow step. So that's why in the slow step, all the 3 molecules are involved in this reaction. So one more thing, this Cn, what is the use of Cn minus in this reaction? Cn, cyanidine, acts as a good nucleophile as well as best leaving group. In the place of cyanide, if you take hydroxide or ethoxide, this reaction doesn't favors proceeds considerably, because so cyanidine is strong nucleophile and also good leaving agent. So this reagent has to leave at the final step. That's why cyanide, in this case, cyanide acts as fits good for this reaction. So this is the reaction mechanism. In the first step, what is happening? Cyanide is adding to the carbonyl carbon, then proton abstracting proton and losing one proton by getting carbanion. This carbanion is stabilized by resonance. So this minus charge is delocalized. So you see minus charge is coming to here, cyanide minus triple bond, pi bond is reducing here. Due to this delocalization, we are getting one more structure like this. So it is resonance stabilized. That's why the formed carbanion is more stable. So in this reaction, one molecule is acting as donor. Another molecule of benzaldehyde is acting as acceptor. So donor, acceptor, 2 molecules acting differently. Okay, so a donor molecule acts as a carbanion, acceptor molecule acts as an electrophilic reagent, electrophilic center. That's why reaction proceeds in such a manner to give benzoin, alpha hydroxy ketone, which is also called as benzoin. This is the reaction mechanism for benzoin reaction. So some characteristic points. Potassium cyanide or sodium cyanide is used as catalyst in this reaction. Not only KCN, we can use NaCN also. Anyhow, these compounds generate cyanidine, which is a good nucleophile and best leaving group. This is a very important one. Cyanide acts as a good nucleophile and best leaving group. So reaction rate is proportional to You see, this is the rate equation. So benzyl molecules is to the power of 2 and a cyanide molecule. That's why order of the reaction is 3. Okay. Then, so in this reaction, as we already discussed, one molecule carbanion is one molecule which is connected to carbanion acts as donor. Why? Because donor. Why it is donor? It is electron donating to the another molecule of benzaldehyde. That's why it is donor. Another molecule is accepting electrons from other molecule. That's why it is an acceptor. It is a donor in terms of electrons. So, okay, one more thing. Carbanion. It's a carbanion. Carbanion is more nucleophilic when this benzene group contains plus M group. So electron releasing groups like plus M or plus I groups whenever in the benzene molecule, generally a reaction favors. That means corresponding aldehyde acts as good donor. In other case, if the molecule of benzaldehyde has electron withdrawing groups like minus M, minus I groups, this type of aromatic aldehyde molecule acts as good acceptor. So in the case of two different aldehydes, which one acts as donor, which one acts as acceptor depends in this content. This is this issue. So whether a benzaldehyde or aromatic aldehyde contains electron releasing groups, plus M groups like methoxy or dimethylamine like groups, it favorably acts as donor, electron donor. That means the corresponding carbanion is more stable. That's why the molecule converted to carbanion. So another molecule which is having electron withdrawing groups acts as acceptor because more electrophilic nature of carbonyl carbon in those molecules which have minus M groups. So one thing I can say plus M groups, aromatic aldehyde with plus M groups acts as donor, aromatic aldehyde with minus M groups as acceptor in wherever two types of aromatic aldehydes are there. Some more examples. So and applications. If benzaldehyde in presence of potassium cyanide, ethanolic cation, we know that it is a benzoin. This benzoin on oxidation it gives benzylic acid, benzyl on reaction with base it is giving benzylic acid. These are the different synthetic importance of this reaction. So these are compounds having different these are used in different synthetic reactions. So one more example is furfural. Furfural is also an aromatic aldehyde which doesn't have any alpha hydrogen. So this furfural, two molecules undergo condensation reaction in presence of cyanide ion, that means NaCN or KCN in ethanolic solution and water. It is giving furoin. It is like benzoin. So you see beta hydroxy 1 ketone, aromatic ketone. So it's a furoin. So one more example. You see these two are benzaldehydes. This one benzaldehyde, this one also benzaldehyde. But this group is attached with NO2. This group is having dimethylamine group. Just now we discussed this is a plus M group, this is a minus M group. So plus M group, the aromatic aldehyde which has plus M group acts as donor, and aromatic aldehyde with minus M groups acts as acceptor. So in this reaction we will expect two types of compounds. So this one and this one. You see this one and this one. This one and this one. So this is not possible. Why? Because so you see aromatic aldehyde with the electron releasing group like dimethylamine acts as what? Donor. That's why this compound becomes ketone. And aromatic aldehyde with electron withdrawing nitro group, it acts as acceptor, it converts into alcohol. So that's why this compound is only possible, this compound is not possible in this reaction. So this is in the case of mixed aromatic aldehydes. So this is something about benzoin condensation. So one more example, you see aromatic aldehyde which is having 4 pharmal groups. When it adds to glyaxal, you see aldehyde group, 2 pharmal groups attached there, you call it glyaxal. This glyaxal, when it adds to this tripharmyl benzaldehyde or tetrapharmyl benzene in presence of potassium cyanide, you see a beautiful reaction takes place. It forms a tricyclic compound. If you read the exam, if you read the mechanism, you understood the reaction. I am not going to write any mechanism. If you try, this is a homework for you. Try to write the mechanism for this reaction. So I am giving you one hint. This 2 cyanide ions attacks these 2 carbonyl groups. One thing, and 2 glyaxal molecules attacks. One is from here, one is from here, and one is from here. That's why you'll get a tricyclic compound. So one more example for benzoin condensation. You see pharmyl furan and pharmyl pyrrole. So these two is having, okay, and whenever they react with alcoholic cation, we will expect 2 types of compounds. One is this one and this one. So only this reaction, this compound doesn't form, this compound only forms. Why? Because I have already told, I explained just now, whenever a compound with a high electronegative atom like oxygen, it doesn't willing to provide electrons. That's why this compound doesn't act as carbanion or nucleophile. It acts as a electrophile because of O minus or high electronegative atom. When we compare to nitrogen, nitrogen is less electronegative than oxygen. That's why it acts as donor, it acts as acceptor. That's why we expect only this type of a product. No this compound. So this is due to electron releasing nature of nitrogen, electron attracting nature of oxygen. This is about benzoin condensation. So recap, what is benzoin reaction? So condensation of 2 or similar or different aromatic aldehydes in presence of cyanide nucleophile at the alcoholic cyanide, it gives a alpha hydroxy ketone which is called benzoin. This is the benzoin reaction. We have discussed different examples for benzoin reactions involving furfural and other compounds, and we discussed mechanism of this benzoin condensation. So we'll go to next reaction. It's a Perkin reaction. You see, it's a Perkin reaction. Perkin. This reaction is named after a scientist named William Henry Perkin, who developed this reaction. So Perkin, William Henry Perkin, he proposed and updated. He developed this reaction. That's why his name is a Perkin reaction, the name of scientist. So what is Perkin reaction? What is the mechanism? We'll discuss step by step. So first, what is Perkin reaction? So aromatic aldehydes, when heated with the anhydride of an aliphatic acid in presence of sodium salt of acid, sodium or potassium acid, in condensation reaction forming alpha beta unsaturated acid. Okay, so this is also a reaction of aromatic aldehydes without having alpha hydrogens. One thing. Second thing is in presence of acetic anhydride. This is also reactant substrate. So whenever aromatic aldehyde react with anhydride which containing alpha hydrogen, that is important. In presence of strong base like sodium acetate, it gives a product. On hydrolysis, finally it gives a stable product. So for example, if you detail example, you see This is aromatic aldehyde. It's a benzaldehyde. When it reacts with the acetic anhydride, you see this is acetic anhydride. Acetic anhydride. This acetic anhydride, when react with sodium acetate, this is sodium acetate. Okay. When the reaction proceeds to give cinnamic acid, you see this is a cinnamic acid. Cinnamic acid. This cinnamic acid is alpha beta unsaturated acid. Why alpha beta? How can we say this is a functional group? It's alpha carbon, it's a beta carbon. So in between alpha and beta we have double bond. That's why it is called alpha beta unsaturated acid. It is called cinnamic acid. It is a product in Perkin reaction. Acetic acid is a byproduct of this reaction. So this is a net reaction. What is the reaction? Benzaldehyde, when reacts with the acetic anhydride, not only acetic anhydride, any anhydrides which is having alpha hydrogen in presence of strong base like sodium acetate, it gives cinnamic acid or concerned derivative of cinnamic acid plus acid of corresponding anhydride. This is a Perkin reaction. It's clear. So Perkin reaction, what is happening? In Perkin reaction, aromatic aldehyde is reacting with anhydride in presence of base, giving a alpha beta unsaturated ester, which is on hydrolysis, finally gives a alpha beta unsaturated acid. So this is an example for Perkin reaction. Okay. Then one more example for Perkin reaction. You see aromatic aldehyde, benzaldehyde, when reacted with propanoic anhydride, you see it's a propanoic acid, CH3, CH2, CH2, CH3, CH2, COOH. So anhydride means when two propanoic acid combines together by eliminating water, we get propanoic acid anhydride, propanoic anhydride. In presence of sodium salt of acetic acid or potassium salt of acetic acid, we are getting this derivative of cinnamic acid. So 2-methyl cinnamic acid. Why it is changed? It is why we have used instead of acetic anhydride, we have taken propanoic anhydride. So this is the one example for what? This is also one example for a Perkin reaction. So one more example, third example is a furfural for 2-formyl furan. It's called furfural. Furfural in presence of acetic anhydride, CH3CO twice is also called acetic anhydride. In presence of sodium acetate, it is giving, you see, furoic acid. So this is called furoic acid with plus acetic acid. So these three examples are examples for Perkin reaction. One is what? Benzaldehyde with acetic anhydride giving cinnamic acid. Second, benzaldehyde with propanoic anhydride giving methyl cinnamic acid, and other is furfural with acetic anhydride in presence of sodium acetate, it is giving furoic acid. Like cinnamic acid, it is furoic acid. No? Okay. Then coming to the mechanism, we will discuss mechanism. Okay. This reaction is stepwise reaction. In step 1, carbanion generation taking place. Carbanion. So first sodium acetate ionizes to give acetate ion and sodium ion. This is the first step. So acetate ion and sodium ion. This acetate ion abstracts a proton from anhydride. You see carefully, this is acetate ion, which is a strong base. Why? Because acetic acid is weak acid. Weak acid conjugate base is strong. That's why it's a strong base. Strong base easily abstracts a proton whenever possible. These three, CH3, this CH3, both are similar. Both are same acidic value. That's why one of the ion is abstracted by our this acetate ion, which is a strong base. So after abstracting acetate ion, it forms its corresponding carbanion ion. You see, this is a carbanion ion. This is a carbon. Why? Because carbon with minus charge. Due to loss of proton, it formed its corresponding carbon. So this carbon is stabilized by resonance. You see, electron delocalization is possible. This electron is moving here. At the same time, this pi bond is moving here due to oxygen electronegativity. So that's why we expect these two types of resonance structures, this one and this one. So hence we can say it is stabilized. Whenever an ion, a reaction intermediate is possible in more than one form due to electron delocalization, we can say that phenomena is called resonance. So whenever we write more resonance possible structures, more stable. That's why this is more stable. Carbanion is generated. It acts as a carbanion. This is a carbanion. Okay. So in the first step, what is happening? What happened? A state ion attracted a proton from acetic anhydride. It formed corresponding stabilized carbanion. This is a carbanion. This is the first step. Going to second step. In the second step, this carbanion, acetic anhydride carbanion, requires electrophilic center. It's a nucleophile, we know that. In benzaldehyde, another molecule of benzaldehyde, this carbon, electrophilic carbon, it is acts as electrophilic center. So this nucleophile attacks this carbon. Why this carbon? This carbon is electrophilic in nature because of oxygen, high electronegativity. Pi bond mobilizes towards oxygen, delocalizes towards oxygen. Okay, then what happens? This structure forms, you see. So carbon-carbon bond is formed. New carbon-carbon bond is formed. You see, this bond is formed. It is a new bond. Two molecules get attached. So then this O minus is nucleophilic in nature, basic in nature. It abstracts a proton from this acetic acid by forming this hydroxy compound, hydroxy ester. So whenever this O minus abstracts proton from acetic acid by forming this hydroxy compound. This hydroxy compound, on heating, it easily undergo dehydration reaction by losing one water molecule. It forms a double bond compound. What is the driving force for this reaction? You see, in this product, we observing a conjugation. You observe carefully: double bond, single bond, double bond, single bond, double bond. It is called extended conjugation. Due to extended conjugation, there is a delocalization electron taking place. That's why it is in more resonance structures. We can write resonance structures for this ion too. That's why it is stable. So this is the driving force for this reaction. So we can say this compound is more stable than this. Why? Because having extended condition. That's why small amount of heat, if you supply, readily undergo dehydration reaction by forming this type of ester. This ester on acidic water, acid conditions, undergo hydrolysis reaction. How? This COO bond undergo lysis, fission in presence of water. OH is attached to here, H is attached to here. So we know ester hydrolysis will get acid and alcohol. We know. But it's anhydride. So anhydride hydrolysis is giving both acids. One is this one, our product, cinnamic acid. Other one is, okay, one is cinnamic acid, other is acetic acid. These two acids, anhydrates on hydrolysis will get two acids we studied in the previous class. So this is a Perkin reaction mechanism. Very easy one. So in the first step, what happens? In the first step, once again I repeat, in the first step, this acetate ion, which is a strong base, it abstracts proton from acetic anhydride by forming a carbanion, which is stabilized by resonance. Okay, this resonance stabilized carbanion attacks another aldehyde molecule. You see, another aldehyde molecule, we're getting a addition product. anion, a O minus with O minus, which is also unstable. It abstracts proton from acid by giving this compound. So this compound on heating, it forms more stable conjugated ester on dehydration reaction. So that's why it is stable by resonance, by conjugation. This resonance, this stable ester anhydride undergo acidic hydrolysis in place of water. It is giving hydrolyzed product as two acids. One is cinnamic acid and ester. This is the mechanism of what? It's a mechanism of Perkin reaction. So far we have discussed. Once again I recap. So we are studying reactions and organic named reactions involving carbanion. In this episode, in this lecture, we discussed two types of reactions. One is benzoin condensation. Second one is Perkin reaction. Benzoin reaction and Perkin reaction, both reactions are exhibited by aromatic aldehydes. Both aldehydes doesn't have any alpha hydrogen. In benzoin condensation, what happens? Cyanide is a catalyst, a reactive catalyst. In presence of cyanide, two types of aldehydes or similar type of aldehydes participates in the reaction. So aromatic aldehydes in presence of cyanide catalyst, in presence of alcohol and water, it gives a alpha hydroxy ketone, which is also called benzoin. Benzoin is a specific product. It has some synthetic importance. We can convert this benzoin into different compounds. That's why we use this reaction in different synthetic industries. Cyanide. Why we are using cyanide in this reaction is very important. In some exams, it is asked why cyanide is required. We can, in the place of cyanide, we can use hydroxide or ethoxide. No. If we use cyanide, if we use other nucleophile other than cyanide, this reaction doesn't take place favorably. Why? Because cyanide is a nucleophile, a good nucleophile as well as a good leaving group. So we have discussed the mechanism and we learned that electron releasing groups, a compound, organic aromatic aldehyde with electron releasing groups, it acts as an electron donor. In other words, aromatic aldehyde with electron withdrawing groups acts as electron acceptor. So that means donor and a reaction is taking place between donor and acceptor. So donor group is converting into keto group and the acceptor group is converting into alcohol group. So in benzoin we have two groups, alpha hydroxy ketone. Hydroxy group is there, keto group is there. Okay, so that's a benzoin condensation reaction. We discussed then Perkin reaction. Perkin reaction is also a reaction in which a carbanion acts as a reaction intermediate. So carbanion based synthesis. In this reaction also new carbon-carbon bond formation takes place. In this reaction, aromatic aldehydes in presence of base like a sodium acetate or potassium acetate, when it reacts with anhydrides, it gives a alpha beta acids. So first in this reaction, first carbanion when we see the mechanism, first step, carbanion formation takes place. The formed carbanion is stabilized by resonance. This resonance stabilized carbanion attacks on benzaldehyde molecule or aromatic aldehyde molecule by giving a O minus ion, followed by proton abstraction from acid. It forms an hydroxy compound. On heating, eliminating water molecule, it gives a double bonded alpha beta unsaturated anhydride. It's also an ester. So this anhydride on presence of acidic water hydrolysis, finally it gives acid. So in this way Perkin reaction takes place. So Perkin reaction and benzoin condition, both reactions are involving in both reactions carbanion is involved as a reaction intermediate. So thank you very much. We'll see in the next class. In next class we have two more reactions in this chapter. One is a haloform reaction and the other one is synthesis of higher alkynes. So we have two more subtopics. With the topics we'll close the chapter. So we'll see in the next episode, that is carbanions part 4. Thank you very much.